from this computer and then share. Okay, so let's restart on the example 5. Okay, example 5 is how to determine the fugacity coefficient as well as fugacity in the solution. Okay, component in the solutions. Previously we already calculate fugacity and fugacity coefficient for the pure species. Okay, we did the tutorial also together. Now we are going to calculate the fugacity and fugacity coefficient for two species for binary system. Okay. Here, if you remember, we only apply method of the virial equations. Okay, this is only that we cover for this part actually. Okay, if you look at here, for the species in solution, we have to apply this equation, second virial equation. Okay, you have to remember B11. Okay, B22 is for pure species. B12 is the mixture of components. Okay, omega 12, TC12, PC12, VC12, and ZC12. Since this one is for the mixture. Okay, so please remember at least there's a two component. Okay, binary is for the two components. If more than that, it's gonna be 3 components or 4 components is depending on the mixture. But I think we only cover for the binary mixture. I think. Okay. So this is general equation, the important one. Okay, B omega TC PC VC ZC, as well as you have to calculate the value ln phi. Okay, ln phi1 and phi2. Okay, as well as you need to determine also the delta. Okay, before to calculate the ln gamma 1 and gamma ln phi1 as well as ln phi2, which is represent as fugacity coefficient. Once you determine the fugacity coefficient, we can calculate the fugacity species in solution for species 1 as well as species 2. Okay, so to calculate the fugacity, we have to use this equation. Okay, as the annotated. You have to use this equation to calculate the fugacity species in solution. Okay. Okay. So next, we do the tutorial, which is this tutorial, example 5, or we do together. Estimate fugacity coefficients for species 1 in solution as well as fugacity 2 species for species 2 in solution for an equimula. Equimula, that means 0.5 fraction is 0.5 for species 1 and species 2 also 0.5. Okay. Of the methyl ethyl ketone for the species 1, toluene for species 2 at 50 degrees C as well as the pressure is 25 kilopascal. Set all Kij equal to 0. Okay, Kij actually is the parameter of constant interaction. Okay, okay. Actually, if it's not given, okay, you can do assumption Kij equal to 0. If it's given, you have to use it to calculate TCij. Okay, you have to calculate the critical temperature. Okay, for both components. Okay, how can we start? Okay, so first you have to construct the table. Okay, so for species 1, this is a species 1. Okay, and this one is a species 2. Okay, and T is equal to 50 degrees C. Okay, this one is 50 degrees C. Okay, pressure equal to 25 kilopascal. Okay, equal to 0.2467 bar. Okay, 0.2467 bar. Okay. Okay, this one in kilopascal lah. 3.15 Kelvin kilopascal. Okay. So it's already stated Kij is equal to 0. So what you have to do is you have to construct table. Okay. So you have to construct table something like this. Okay. really ni pula. Okay. So this one is for the component ij. Okay. So please remember, okay, 1 is pure species, 2 pure species, 1 mixture. Okay. So we have to calculate this one. Okay. Okay. And then this one you have to calculate TCIJ. Okay. TCIJ. Okay. PCIJ. Constructible. Okay. And then VCIJ. Okay. ZCIJ. As well as omega ij. Okay. So how to calculate TCIJ, PCIJ, VCIJ, and ZCIJ as well as the omega ij. So if you want to calculate, you refer to this equation. Okay. So Bij equal to R TCIJ, and this one is for omega, TCIJ, PCIJ, VCIJ, and ZCIJ. That's how to calculate. Okay. So if you calculate TCIJ, actually TCIJ in the equation is equal to TCI, okay, TCJ, okay, power of half, okay, right, 1 minus KI Ij. But this one equal to 0. Okay, this one is TCIJ. So if TCI I is equal to 1, okay, J is equal to 2. So TC1 and TC2. So that means this one is 4, 1. This one is 4, 1. Oh no. So that. Okay. This one is TC1 and TC2. This is power of half. So can you calculate the TCIJ? So you have to calculate for this one. Okay. This one is you have to determine from the appendix. Okay. If you look at in appendix, okay, since this is pure species for methyl ethyl ketone, right? This is for methyl ethyl ketone. So please find TC11 or equal to TC1. So this one is TC1 and this one TC22. Okay, so that means this one T2. So for T2 is equal to toluene. Okay, this one. So please determine from the appendix. Once you determine TC1 and TC2, just substitute into equation of TCIJ, TC1 and TC2. So please calculate. Okay, and then you have to calculate VCIJ first because PCIJ you need information. If you look at here from the equation, okay, you look at here from the equation for the PCIJ, okay, for the PCIJ, the equation is equal to ZIC ZIJ Z12, okay, Z12 R TC12 divided by VC12. So that means we need to determine ZC12 first. Okay, ZC12, RTC12, and VC12 first. So that's why we have to determine VC, ZC, and omega first. Okay, so this one you have to determine from the tables, appendix. Okay, this one from appendix. Please determine from the appendix. Okay, for the methyl ethyl ketone as well as toluene. I think it's the appendix B. Okay, so please determine first. And then you have to calculate PC, VCIJ, and ZCIJ. Okay, so please determine. So I give you the full informations in the WhatsApp. Okay, please refer to the WhatsApp. Okay. So please determine the TCIJ. Okay, so that's the tables, and then when you determines the all the critical value. Okay, so this is the answer. Okay, so what you have to do, you have to calculate this one. Okay, please determine from the equation. So I need the answer. What's the answer? So this one is based on the equation here, the previous equation. So that means W12, W1 plus omega 2, TC12, PC12, VC12, ZC12. Just substitute from the value that you obtain from the table for component 1, this one, and component 2, this one. This one is from table appendix. This one you have to calculate. Okay, you have to calculate this one. So you calculate already? So once you calculate, okay, so you can please refer to the WhatsApp. That's the value. Okay. So for TC12 is equal to 563 kelvins. Okay. PCIJ is equal to 41.3 bar. Okay. And VCIJ 291 cubic centimeter per mole. ZC 0.256 as well as omega ij is equal to 0.2993. So next, what you have to do is you have to construct another table since we need the information of beta. B, not beta. B, this one. Okay, this one. Okay, because you need information this one to calculate delta. Okay, this delta. Because your equation need a B11 delta, also B22 as well as delta. Okay, so you need this information. Okay, that's why we have to use Villiers equation. Okay, so similarly you have to construct the tables. Okay, you have to construct the tables. Okay, this one, and then 1 1 1 2 1 3 1 2 3 4. Okay, and then ij similarly omega. Okay, so this one is ij, okay, trij, b naught, b prime, as well as b I j. Okay, so this one is for component, pure component 1 1. This one is for 2. Okay, this one is 1 2. Okay, so trij, if you remember, TC for metal articulation is equal to, if you determine from the appendix, is 535, okay, 0.5 Kelvin, while for toluene is 591.8 Kelvin. Okay, so just substitute. Okay, just calculate based on the this one, based on the information is given. Okay, 50 degrees C is equal to 332. 332 also difficult. 5 divided by TC. This one 500 to 5. 500 to 5.5. So you can get TR for 1 1. Okay. Similarly, also for toluene. Toluene is 3 to 5, 3 to 3. Okay. 50 degrees C, 3 to 3 Kelvin divided by TC from appendix 599. This one. Okay. So you can get TR. Okay. And then for 12, TR12, which is a mixture. Okay. So if you look at here, 3 to 3.15 divided by from the previous table that we calculate from the pure component. Okay, temperature, critical temperature TC1, 1 to TC1 to that you calculated. Okay, okay, so that is for TR. Okay, similarly also B naught. Okay, B naught. This equation is, I think all of you already know, 0.083. This one is already given in chapter 3. Okay, 0.422 divided by TR power of 1.6. Okay, so you have to calculate this one, as well as this one. So TR is given already. TR just substitute into this equation. B1 is equal to 0.139, okay, divide 0.172. TR 4.2. Okay, this one. Okay, that's the value. And Bij, okay, Bij you have to calculate from the equation, from the previous equation, this one. So you have to calculate this one by using this one. Okay, so that means Bij equal to RTCij. Okay, Bij is equal to TCRij. TCij. Okay, RTCij. Okay, divided by PCIJ P naught K plus omega ij B prime. Okay, so you can calculate this one. So if that means for component 11, TC11 divided by B divided by PC, okay, PC11 times with B naught plus omega 11 B prime. This one also TC22 and this one TC12. So you can calculate all the components. So please calculate, guys. Okay. Are you done? Hope you can calculate. Okay, if you calculate, please refer to the WhatsApp. So that's the value that once you calculated all the TRIJ, B0, B1 as well as BIJ. Okay. So what's next? What you have to do? You have to calculate. You have to calculate. Please remember what we have to calculate next. We have to calculate this one. Okay. This one. Delta IK or delta 1, 2. Okay. Since it's a two component, delta 1, 2 equal to 2B1, 2. Okay. B11 minus B2, 2. Okay. So we have to calculate that one. So how to calculate that one? Delta 1, 2 equal to 2B12. This one we determine from the previous tables. B11 minus B22. Okay, this one we determine already. Okay, let's remember this determine, this one determine, and this one determine. So please calculate the value of their delta. So you can determine delta 1, 1, 2 from the previous table. Okay, once you determine, so the unit is centimeter, cubic centimeter. Okay. Okay. So we determine already all the information. What's next is we have to calculate this one. Okay. So if you look at here, we calculated already this one. this one, okay, this one also, this one, okay, and this one is equimolar, equal to 0.5, okay, so that you can calculate ln gamma 1 and ln gamma, ln phi1 and ln phi2, okay, Fogarty coefficient species in solution for species 1 as well as species 2. So please calculate. Okay. So once you calculate phi phi1 as well as phi2, okay. Okay, this one you determine already. So you have to determine. Oh, it's stated only what is it? Estimate only phi1 and phi2. Okay, so you already determine the answer. Okay, but if it's stated, you have to determine the Fogarty. Okay, so you have to use this equation. Okay, if it's stated, you have to determine the Fogarty. F tu mak siapa tu panggil? Mak siapa tu panggil? Okay.
Lin.
YI P. Okay, if determine.
Lin, mute Lin.
So if you want to determine Fogarty integration, so Fi. So just you determine already this one equimolar and pressure. Pressure is equal to is given, right? Okay, you can determine. Okay, can you determine? Okay, I hope you can determine all the steps you understand. Okay, so I given the answer. Okay, so that is the answer, which is phi1 is equal to 0.987 from your WhatsApp. Okay, and phi2 is equal to 0.983. Okay, I hope everybody can understand. So could you please do this for the tutorial 3? Similar procedure. Okay, I give you about 10 minutes. I think 10 minutes is enough. So 240. Okay, you stop. Can you? Please do, and I will call who the student maybe can share the answer. Which student can share the answer? So this one is for the system ethylene and propylene. Okay, estimate F1, okay, F2 as well as P1 and P2 at 150 degrees C, P30 bar, and Y1 equal to 0.35. Even this is high pressure, since our topic is only cover the virials, so you just use the virial equation. Okay. So guys, please do. Okay. Please do tutorial 3. First, you have to determine the, what is it? TCIJ, PCIJ, okay. TCIJ, PCIJ, okay. VCIJ, Z C I J square M omega I J. This is the first step. Okay. Second step is TR I J beta naught B1 BI J. Okay. And then you have to calculate the delta I J. Okay. Once you determine delta I J, you can calculate P1, P2, as well as F1, F2. Okay. So for step 1, 2, 3, 4. I think it's 3 steps. This one can be inserted here. Delta. Okay. So please calculate. So saya panggil seorang kan nanti. Mungkin boleh share ataupun boleh you can share or tell me the answer. I think it's share. Okay. Who's here? Participant. Okay. You done? Anyone volunteer to share? Shazlin nanti share. Shazlin share. Okay. So sorry. Okay. Nanti share your what you're going to do. Farid Abdul Rauf. Okay. Dapat? Anyone? Sorry. Okay, dalam grup WhatsApp. Kenapa awak letak dalam grup WhatsApp? Jom. Dekat sini lah, boleh share kat sini. You boleh share sini. Grup WhatsApp pun boleh juga, nanti saya letak kat sini. Ataupun you nak share dekat sini ke? Kat WhatsApp awak tu kan? Okay. So you can send to the WhatsApp. Okay. So saya share kat sini. I will share here. It's okay, just send to the WhatsApp. I will share. Hello. Okay, okay. So just give me the answer for what is it? For the TCIJ, PCIJ, VCIJ, you just give me the value. What's the value, Shazli? Let me check again. To message. Okay, so it's okay. So please check your answer. TCIJ, TCIJ. Okay. So please refer to the WhatsApp. Saya akan upload. Okay. So that is the value for TCIJ, PCIJ, VCIJ, ZCIJ, and omega IJ. Okay. And then B naught and B not okay. And that one is a TRIJ, B naught, B prime, and BIJ. Okay. And then the delta. So please check your answer. And this one is for delta. Okay. How about phi1, phi2, Fugas T1 and Fugas T2? Who can give me the answer? Tashini. Answer? Phi1, phi2. Have you done? Tak ada jawapan. Anyone? Oh, Nisha. Phi1, phi2. And Fugas T1, Fugas T2. What's the answer? You can write. Animesh, what is this? Fugas T1, 0.9574. Okay, 0.9574. Okay, that one is not Fugas T, okay? That one is the Fugas T coefficient. Fugas T coefficient, phi1 equal to 0.9574. Okay, Animesh. And phi2 is equal to 0.875. Okay, so from Fugas T coefficients, after that you have to calculate the Fugas T. Okay, please remember that. Okay, it's different between Fugas T coefficient as well as Fugas T. Okay, so this is the full answer. Okay, so I given already the answer. So I hope you can do this one. Generally, the question for the test is similarly like this. Okay. Okay, any questions? Okay, so this one is for the three component. I don't think we will cover this. It's gonna take a very long calculations. Okay, it's quite difficult. Okay, so let's move to the ideal solutions. Okay, what is the ideal solutions? Okay, so previously there is a gas, ideal gas, right? It's almost similar. Ideal solution is for the liquid. Okay, so if you look at here, we know that the ideal gas mixture, okay, no molecular force or interaction. Okay, the assumption is no molecular force or interaction for the ideal gas, and negligible the particle volume. Okay, so that means the chemical potentials here is equal to G plus RT ln yi. The fraction is by using yi. However, for the ideal solution is there is exists the intermolecular interaction, but the various molecules have similar size, structure, and intermolecular force. So for the example, hydrocarbon, okay, N-hexane and I-hexane, okay, or no, what is the longer change? N-propane and I-propane, or what else? The isomer, right? Okay, so we can do assumption also like a propane and butane, okay. They have a almost similar size structure, okay, but they are similar, okay, but different with the ideal gas mixture, because ideal gas mixture there's a no molecular force or interaction. There's for the solution there is a intermolecular interaction, but the molecule is similar size structure and also similar the intermolecular force. That's the assumption for the ideal solution. Actually, it's the basis for the calculation of the non-ideal solution. Okay, if you look at here, they're applicable for real gas mixture and liquid solution. However, application is most often to the liquid solution. So you have to remember that, because this part is going to be related with the chapter 12. So we have to determine, if you remember, this chapter we calculate it, we determines the fugacity of the gas phase, mostly the gas phase. Okay, that's why we determines uh, the the fugacity by using the fugacity coefficient. But in chapter 5, we mostly focus on the solution or liquid. Okay, we have to determine the fugacity of the liquid based on the activity coefficient. The symbol is gamma. Okay, since in equilibrium fugacity in vapor and liquid is similar. Okay, thus for the ideal solution, GID is equal to, okay, XI, the partial gives energy for ideal solution equal to XIGI plus RT, so sum of the XI ln XI. So this is the gives energy for the ideal solution. Okay, so for the entropy, okay, SID, you have to remember this equation. This one is for the gives energy. You have to remember this equation, highlight in your textbook, okay, as well as SID is equal to XISI minus R sum of XI at ln SI. This one is for the ideal solution. You have to remember this is the criteria. Okay. While for the enthalpy and molar volume is HID equal to sum of XI while VID is equal to XIV by I. This is the equation, the important equation. Okay. So this is actually the basis for the calculation of the non-ideal solution. We have to remember, if for the non-ideal gas, the basis or the reference is the ideal gas. Okay, but for the non-ideal solution, the basis or the reference is the ideal solution. Okay, so you have to remember that. Okay, so for non-ideal solution, okay, non-ideal solution. Okay, the real solution is evaluated with the reference to the ideal gas mixture or real gas lah. Okay, by using the definition of residual properties. Okay, so you remember we calculate the residual properties in chapter 4. Okay, mostly that one is for the gas phase or for the only not the mixture, which is only for the one component or one phase. Okay. Hence, the following equation is generally and easily applied for the gas mixture, only for the gas mixture, the residual. Okay. Real liquid solution is, however, much more convenient to be evaluated with the reference to its departure from an ideal solution. So that's mean for not ideal gas. Okay. So as a reference, which is a ideal solution. Okay, so liquid solution we calculate from the departure from the ideal solution. For the reference is ideal solution. Okay, how to calculate that one? So we introduce another properties. We call it as we call it as excess properties. Almost similar like residual properties, but not similar. Okay, since excess properties is only available for the mixture or for the solution. Okay, so hence we define an excess properties. This is what we call it, the difference between actual properties of a solution and the properties of an ideal solution at the same temperature, pressure, as well as composition. So ME equal to M minus MI ID. Okay. Similarly, if you remember for the residual, MR equal to M minus MIG. That one is for the gas mixture. Okay. Only for the excess is only applicable for the solution. Okay. Okay. So for example, H equal to HE plus HID. This one, if you rearrange again, since for the real non-ideal solution, M equal to ME plus MIID, so that you can get the real solution. So for the enthalpy, H equal to HE plus HID. Now let's apply this definition to the Gibbs energy. What happens to the Gibbs energy? What's the relationship between Gibbs energy? Okay. Previously, the residual Gibbs energy is related to the Fugate coefficient, right? Okay, the partial residual Gibbs energy is the definition for the Fugate coefficient. Okay, if you look at here that this is just derivations. Okay, just derivation for the excess Gibbs energy. We can see here that partial Gibbs energy, okay, excess Gibbs energy equal to RT ln Fi divided by Fi. This one is for the component species in solution. This one is for the pure species. Okay, this one is the fraction in liquid or solution. So we can see here that there's another another properties or parameter. What we call it here is we call it as the activity coefficient. Okay, we call it as activity coefficient. This one. Okay, this one is activity coefficient for the solution. Okay, so it's almost similar, right? Okay, so for the gas we calculate by using for the gas we calculate we use the Fugate coefficient, but for the solution or for the liquid we use the activity coefficient. Okay, so to determine the fugacity of the species in solution, okay, so we have to times with the gamma I, this one. Okay, gamma I. For previously we use P I. Okay, if you remember, right? Okay, and then yi times with p. Okay, so that's how to determine. Okay, so next, so for the ideal solution, if you look at here, you have to remember the fugacity actually, the fugacity of the ideal solution species in solution actually XIF actually is follow the Lewis Randall rules. Okay, Lewis Randall, that means really ideal. Okay, if non-ideals, the graph will be actually is deviate from the ideal solution. Okay, also divided by pxy. So we can see here that the fugacity coefficient actually is similar. Okay, fugacity coefficient of species I in ideal solution is equal to fugacity coefficient of the pure species. Okay, so this is the criteria for the ideal solution. Okay, so let's see the important of thermodynamic properties here for the fundamental excess properties relation. Okay, this is just the derivation. This is the definition that I told you that the activity coefficient actually is the partial excess Gibbs energy. Okay, ln gamma is a partial excess Gibbs partial properties of excess Gibbs energy divided by RT. So also important is the composition. Okay. So previously, if fugacity coefficient is the residuals, okay, is the partial properties of the residual Gibbs energy, but for the activity coefficient is the partial property of the excess Gibbs energy. Almost similar. Okay. Okay. So let's move. Okay, this is the important one for the calculate the excess Gibbs energy. So you have to calculate this one. You have to highlight. Okay, xi ln gamma I. Okay. So xi ln gamma I equal to 0. Okay. So the equation is important in phase equilibrium thermodynamics. Okay. Okay. So this is the relationship between residual properties as well as excess properties. Okay, look at here that for the m's, this is for the general, right? H equal to G plus Ts, right? But for residual, HR, GR plus TR. For excess is HE equal to GE plus TS. It's almost similar. Only the symbol is different. Okay. That means excess is for the solution, residual is for the gas. Okay. The symbol is the relationship is almost similar. Okay, for the enthalpy against energy for the entropy, only the symbol is different. Okay. Okay. So if you look at here that if in vapor in liquid equilibrium, okay, for vapor mixture, okay, you look at here, right? Okay, FIV, okay, this one you calculate in this chapter 11. For the liquid solution, actually FIL equal to gamma I xi P. So how can we calculate this gamma I? Okay, this is we will calculate in chapter 12. Okay, how to determine? Okay, generally we will use graph method or direct method. There's a two method actually. Okay, so we will discuss next week. Okay, however for the BLE criteria, which is in equilibrium, vapor and liquid is similar to gas, right? So that means this one is for the gas, this one is for the liquid. It's similar. Okay, since the fluidity is similar, this is the VLE relation that relate to the composition of vapor phase and the liquid phase. This one is for liquid, this one is for gas. Okay, so since actually if you want to calculate the gamma, we need the relationship of the other. I mean, you need this information actually. Okay, we need information. But if your gas mixture is ideal, this is equal to 1. Okay, generally we do assumption this one is equal to 1. Okay, if not ideals, you have to calculate the gamma and the phi one of Fourier coefficient before you determine the gamma I. Okay, this one actually the fraction is determined from the experiment. This is actually is from the data. It's a given. The problem is to determine this one. Okay, and also this one. Okay, generally we will determine this one first, and then we will determine the activity coefficient. This is what we gonna discuss in chapter 12. Okay, and the application is actually in chapter 10. Okay, how to use this gamma as well as phi. Okay, so we almost finished. Okay, this is the nature of the excess properties. If you look at here, this is the graph. Okay, look at here is a like a spherical, not spherical. Okay, half of the spherical. Okay, there's a maximum here. Okay, and this is a pure actually. Okay, what else? Look at here, the nature of the SS properties. SS properties become 0 as other species equal to 1, which is approach the purity. GE is a parabolic shape. Okay, parabolic shape is something like this. Okay, this is a parabolic. Extreme value or optimum is actually is equimolar composition. That means this one. This is 0.5, almost 0.5. Okay, this is the properties of the nature. Okay, so this is the summary of the ideal mixture, ideal solution. GID, you have to remember how to calculate SID, VID as well as HID. Okay, okay. So this is the summary. Okay, we already discussed, as well as for the definition of the activity coefficient. Actually, is the partial properties of the excess gate energy. Okay, and how to calculate the gamma. Gamma is in chapter 12 actually. We will calculate this one. How to determine the gamma. Once you determine gamma, you can calculate the fugacity. Okay. So this is the nature of the non-ideal solution. If ideal solutions, you remember that partial gauge energy is equal to 0 and gamma I is equal to 1. That means the fugacity coefficient of ideal solution is equal to fugacity of I. Okay, look at here. This is the criteria for the ideal. That's the ideal. This one. Okay, so that means fugacity coefficient species in solution for the ideal solution is equal to fugacity of the pure species. Okay, So you have to remember that. Okay, so any questions? Okay, so actually there's the examples. If you want to do the examples, we can do together this one. Okay, just a short examples. Okay, if you look at here, I just explain briefly. 2 kilomole per hour of liquid and octane, species 1 are continuously mixed with 4 kilomole per hour of liquid isooctane, species 2. The mixing process occurs at constant temperature and pressure. Mechanical power requirements are negligible. Use an energy balance to determine the rate of heat transfer. What do you think? Rate of the heat transfer. Okay. What do you think? Rate of heat transfer. Q. To determine Q, we have to determine H.
Q.
Okay. So what do you think? What is the rate? What your assumption here? If for the ideal solution. That's me. What is your assumption? Yeah.
Lagi sekali doktor.
Okay, what is your assumption here? Use energy balance to determine the rate of heat transfer. What's your assumption here based on this problem for the ideal solution? How about the heat transfer? Because heat transfer we have to determine from the enthalpy. Is this ideal or non-ideal, this one? That's me.
Rasa ideal lah doktor.
Ideal, why?
Kejap.
Kenapa? Kalau base kepada tadi yang saya kasih information ni. Why? Anyone?
Tak sure doktor.
Angkat hand. Okay, you nak pass kat siapa?
Oh, saya rasa nak pass kat seorang ni bernama Tayalan.
Tayalan. Oh, Tayalan aja. Tayalan, anything? You can also send a message actually if you are shy. Okay. What do you think? This is ideal or non-ideal? Nazmi said it's ideals. So if ideals, what is your assumption? Why is ideals? Tayalan. No comment, doktor. Wah, kau senang jawapan. Okay. Okay lah. Apalah korang ni. Saya baru je explain tadi. Tayan, you nak pass kat siapa ke? Sebelum kita habis ni. Okay. Anyone? You nak pass kat siapa ke? Okay. Okay. If you remember, okay, this is ideal. Why is ideal? We back to the previous slide. Kita tengok ni kan. This is the statement. Okay, there exists intermolecular interaction, but the various molecules have similar size, structure, and intermolecular force. Okay, this is the statement actually. If you look at here, why is ideal? Because N-octane and isooctane is similar chemical structure, almost similar size. That's why it's ideal. Okay, that's your assumption. Okay, this is just the isomer actually. Okay, octane and octane. Okay, no different, not much different. That's why the solution is ideals. Okay, so both is also non-polar. Okay, both non-polar and similar structure, similar size. That's the assumption for the solution. You have to remember for liquid solution. But for the ideal gas, actually no intermolecular interaction. Okay, liquid there is the intermolecular interaction, but similar size, similar intermolecular force. Okay, so that means rate of heat transfer is actually is equal to 0. Okay, because there's no heat of mixing. Okay, if you remember, heat of mixing is equal to 0 for delta H of mixing. Okay, it's mixing of both components. Okay, you remember it's equal to 0. Okay, previous slide before the ideal solution. Okay, use the entropy balance to determine rate of entropy generation. So if you look at here, so just refer to the delta S, okay, equal to negative R times with total xi ln xi. Okay, times with the number of mole. There's a number of mole, right? Yeah. Okay, total mole times number of total mole and T. Okay, so total mole you can calculate the mole number here. Okay, this one also. So find the total mole, you can get the molar flow rate. Okay, so you can get the S delta S or total delta S or total. Okay, so it's easy. Okay, so that's all for today. Okay, next week we will cover chapter 12. Okay, please read briefly. Okay, what is about chapter 12? Okay, because it's become quite difficult. Okay, since for chapter 12, you have to use a graph. I hope you can also use a graph paper as well as Excel. I'm not sure because we have to construct a graph, okay, to determine the gamma, okay, gamma I. That one is first method, and then second method we don't have to use the graph paper, so it's just directly by using the equation, so we can determine the gamma, okay, and then the application in chapter 10. Okay, any questions? Okay, just information for the about the test one. Okay, we have everybody is already agree that we will have a test on the Saturday. Okay, 8 p.m. Okay, at night time until 10 p.m. Okay, so actually is 1 hour, 1 hour 30 minutes. Okay, 1 hour 30 minutes. Okay, so maybe some if you cannot do, maybe I give you an extra times about 50 minutes. So you have another 15 minutes to submit your what is it, your answer through e-learning. Okay, hope you can have ample time. Yeah, ada soalan? Faris ya, apa dia Faris? Okay, apa dia?
Tak ada.
Okay, so
Faris masuk, Faris.
chapter 3 we will cover yeah, ideal gas as well as cubic equation of state, and you have to discuss based on the real data. Okay, how you have to determine real data from the graph, from the figure, from the diagram, and you have to discuss. Okay, based on the answer that you calculate from the ideal gas cubic equation of state as well as generalized correlation. Okay, either for the if cubic equation of state, you have to remember we already discussed about the van der Waals. Okay, soft Radicquang, that's one. Okay, what else? Radicquang, Penrose-Vincent. Okay, and generalized variables. Okay, Lee Kessler. Okay, so once you calculate, you have to compare with the the actual data. Okay, and then for the chapter 4, you have to remember, okay, how to calculate the sensible heat, latent heat, if there is a change in the temperature, change in the phase. Okay, how to use that one, and heat of formation, heat of reaction. If you want to calculate the heat of reaction, you have to determine from the heat of formation. Okay, so generally you have to what is it? Draw the hypothetical part before you calculate the heat, all the heats. Okay, you have to remember that, since once you determine the enthalpy, you can determine the heat transfer at the absorb or desorb. Okay, so I hope you can understand. If there is a change in temperature, you have to use enthalpy, and change in temperature, you have to calculate based on the sensible heat. If there is change in the phase, you have to use the latent heat. Okay, if you want to use latent heat, you can use the Thornton's law. Okay, what else? Clapeyron equations. What else? Watson equation.
Watson.
Okay. I think you already learned actually in mass and energy balance. Another method is what you use the Chang's method, right? If you remember. Okay. But if you use throttle slow, actually the accuracy is not really accurate. Okay, it's just 30% of the accuracy. Okay. Okay, or you can just take from the boiling point of the components. Okay, just take the heat of evaporation there. Okay, or the melting. Okay, any question about that one? There's gonna be change in temperature or change in the phase, definitely, plus with the heat of reaction. Okay, any questions? Ada apa-apa lagi tak?
Doktor, saya nak tanya.
Ya. Yeah.
Kalau yang chapter 4 tu kan.
Chapter 4, okay, chapter 4.
Okay. Kalau dia bagi soalan, ada satu reaction. Okay, dalam reaction tu ada change phase dengan change temperature. Macam mana doktor?
So maksudnya you kena
yang kita nak guna, sensible ataupun latent?
Maksudnya you kena dua-dua lah. Awak bawa, sebab tu awak kena draw apa ni? Draw tepat. Awak bawa ke, contohnya macam ni kan. Change in temperature, contohnya for example, you have water, right? Kan? Okay, water. Vapor. You bring it to the what temperature? For example, 200. Bring it to 100 degrees C, right? 100 degrees C still have no change in phase, isn't it? Isn't it? If it enter at 200 degrees C, betul tak? Okay. So you bring it to 100 degrees C. Okay. 200 to 100 because that is the boiling point. Okay. There's no change in phase, isn't it? Okay. From 100 to what? 100 to what? If exit is a liquid, for example, 30 degrees C. Okay, 30 degrees C. Okay. So,
okay,
100 to what? Another line for the hypothetical part.
Nak tukar jadi liquid lah doktor?
Yes, of course. So that means 100 to 100. 100 to 100 lah.
Oh, sure.
Maksudnya, for example, vapor to vapor change in temperature 200 to 100, isn't it? So 100 to 100, liquid to gas to liquid. That's the hypothetical part. Betul tak? Hello?
Ya, saya lost.
Latent
dia
heat,
masuk.
no change in temperature. Change in phase. Sensible heat, change in temperature. But no change in phase. Yes.
Maksudnya dalam kita punya reaction sekarang ni kita guna air, kan? Okay. Air tu kan dia punya boiling point dia 100 kan?
100, yes.
Maksudnya sekarang ni air masuk dalam reaktor, suhu dia 200. So dia nak keluar jadi 100.
Contohnya dia nak keluar dekat 50 degree C lah. Okay. Betul.
Okay. Betul.
Liquid kan?
Okay, so maksudnya air daripada 200 tu dia kena turn jadi 100
lah. 100 dulu. Sebab situ dia tak ada change in phase kan? Okay.
Okay, so 100 ke 100 lah. Dia akan tukar jadi
100 ke 100. Change in vapor, change in phase, and then change in phase. Vapor to liquid. Okay, and then?
Baru change tu ke 50.
Yes, that's correct.
Okay, faham.
Understand? So that's why you need the hypothetical part. I think the best hypothetical part, chapter 6 also one of the best example change in the phase. Okay, since chapter 4 example, there's only change in temperature actually. Okay, faham tak? Okay.
Faham betul.
If you look at the example 4.8, it's just a change in temperature. Change in temperature. Okay. Any question
Yeah,
more? Okay. If no
terima
questions,
kasih Adan.
okay. Thank you very much, guys. Okay. So
Thank
itu
you
je.
Adan.
Okay.
Thank you, Doktor.
Okay. Thank you.
Thank you, Dr.
Thank you, Doktor.